Thank you for joining us for EMBCA's second Hypersonic Geopolitical Challenges Forum panel discussion. My name is Luke Katsos, EMBCA's president, and I will be co-moderating this panel discussion with Technologist and EMBCA director Eric Hill. Our distinguished panel includes Johnathon Reyes, PhD, founder and CEO of Halo Engines, Brian W. Cole, PhD, Associate Dean for Faculty and Planning at the Eisenhower School, National University, and Rachel Hytovik, a PhD graduate student at the University of Central Florida. The recent use of hypersonic missile by Russia in the Ukraine, as well as North Korea testing various missiles with purported hypersonic capabilities, among others, has triggered the second Hypersonic Forum. These developments and others, for example, the passing on of this technology to unfriendly nations, etc., and the geopolitical significance of the East Mediterranean with everything that is currently going on in the area, make this topic of discussion a very timely one. Hypersonic technology enabling missiles and vehicles to travel at speeds exceeding Mach 5, or roughly 1 mile per second, is revolutionizing modern warfare, presenting significant geopolitical challenges. Rockets have flown at supersonic speeds in space since the 1950s, but the technology that allows hypersonic weapons to fly significant distances and maneuver around threats at high speed is a relatively new phenomenon. These weapons can close in on targets, compressing the battle space in ways that may prove to be a game changer in any new conflict. The U.S. has led the world in hypersonic weapons development through 2014, when certain financial issues, funding issues, forced cuts to hypersonic research and development. Several nations are advancing hypersonic missile programs, including, of course, the United States, Russia, and China, which lead in operational capabilities. We have Russia, China, North Korea, and Iran have hypersonic weapons programs, as do Australia, France, Germany, India, Israel, Japan, and South Korea. And certainly we mentioned, just a second ago about North Korea. Funding in Congress for hypersonic weapons has been relatively restrained. However, both the Pentagon and Congress have shown a growing interest in pursuing the development and near-term deployment of hypersonic systems. This is due in part to the advancements in these technologies in Russia and China mentioned, both of which have a number of hypersonic weapons programs and have also fielded operational hypersonic glide vehicles. Potentially armed, at the same time, these can be potentially armed with nuclear warheads, so it becomes a very dangerous situation. Recent U.S. funding for HSW development has increased significantly across the services, and the outlook appears to be a little bit more positive these days. The hypersonic market and industry is poised to expand in a significant way due to these and other developments, with significant market impacts going forward and in the coming decades. Collaborative efforts have been taking place, for example, with the US, the UK, and Australia, further highlight global interest in these transformative military technologies. One major challenge is the erosion of traditional deterrence frameworks. Hypersonic weapons, due to their speed, maneuverability, and unpredictable flight paths, can bypass current existing missile defense systems, leaving nations vulnerable to surprise attacks. This creates instability in global security and increases the risk of escalation during conflicts. For the US, maintaining a credible deterrent while countering adversarial developments is a critical concern. Globally, China and Russia have already fielded, as we indicated before, hypersonic systems. Russia has used the King-Shao missiles in the Ukraine, demonstrating their tactical ability on infrastructure and command centers, despite questions about cost effectiveness and strategic value. Meanwhile, China's DF-27 hypersonic missile testing has heightened tensions in the Indo-Pacific, showcasing weapons designed to evade current U.S. missile defenses, potentially fueling an arms race and with hypersonic advancements. Russia's Avangard and Chinese DFZF pose direct challenges to U.S. strategic interests. With all of this going on, nations may feel compelled to pursue such technology, further exacerbating proliferation risks. The lack of international norms and agreements governing hypersonic weapons further complicates the landscape. Unlike nuclear weapons, no treaties currently regulate hypersonic technology, making it difficult to establish transparency and trust among nations. For the U.S., leading efforts to create a framework for arms control while ensuring its own technological edge is imperative. In 2024, the U.S. Ramped up its efforts to deploy these technologies, including installing the conventional prompt strike system on its Zumwalt class destroyers. These weapons, designed for long-range precision strikes, are part of a broader $13 billion push to enhance hypersonic capabilities. The first Zumwalt equipped with this system is expected to be operational by 2027 or 2028. Although the U.S. military argues these developments are necessary for deterrence and maintaining technological parity, critics have raised concerns about their high costs and the challenges of defending against these weapons. For instance, the U.S. Hypersonic systems, which rely on conventional warheads, require greater precision than nuclear-equipped counterparts, adding to the technological complexity and expense. We will explore in this panel discussion some of the background and challenges facing the U.S. around the recent developments in hypersonics, as well as the technology and research that is taking place in this area, in addition to the potential deterrence and evolving technologies. I would like at this time to introduce our co-moderator for today's discussion, Eric Hill. Eric is a technologist in the third decade of his exceptional career. He holds a bachelor's degree in computer science engineering from the University of New Hampshire. Early, he was involved with rapid expansion of technological infrastructure and distributed management systems that culminated in the dot-com boom, and later explored and researched data warehousing and analytics to bolster understanding of complex systems analysis. In the last decade, Eric became immersed in advanced automation efforts over critical infrastructure, as well as various areas of cyber and cybersecurity, interfacing with a number of tech industry organizations, and has extensive experience in the defense sector. He specializes in dual-use technologies, providing cyber capabilities to the defense and intelligence community, and has presented at various defense-oriented venues in the U.S. and abroad. His significant and acknowledged volunteer efforts have been youth-centered over these years, and with also a laser focus on STEM pipeline development, mentoring, and empowerment. He is also a volunteer director at EMBCA. Welcome, Eric, and thank you for being with us today.
Well, Lou, thank you for the generous introduction. I'd like to thank our three panelists before I introduce the first. Thank you for attending this discussion between you, because it's your area of focus. Johnathon, who I've been in discussions with, I'd like to introduce him first. Johnathon Reyes obtained his bachelor's, master's, and PhD at the University of Central Florida. This is in Orlando. After his bachelor's degree, he spent some time working in the MTADS and PNVS program, Advanced Electro-Optical Fire Control System, used by AH-64DE Apache helicopter pilots under Lockheed Martin. His newfound knowledge of the capability of optical systems led him wanting to understand more, and sent him back to UCF for graduate studies. There he learned he could combine his passion for engines and the capabilities of optics to advance our understanding of physics. His thesis and dissertation helped develop optical systems and methodologies for capturing combustion species and velocity data inside of high-speed ramjet and detonation combustors at high repetition rates. After graduate school, he supported multiple DoD and industry research projects at the university, developing custom measurement systems and fluid injectors that were to be integrated with real-world hardware. This meant taking laboratory-grade science, software, and hardware in scaling up to production prototype systems. And those that have been involved in those efforts, that is not any small feat. Supporting this technology transition inspired him to join Halo Engines in 2022, a propulsion startup spun off from UCF. To take some of the unique bleeding-edge propulsion concepts they are developing and transforming them into products that will help shape the future of high-speed vehicle systems. Welcome, Johnathon, to our panel, and I will hand that off to you now.
Thank you, thank you. I've actually never heard that bio read out loud, so it's the first time. That was great. So I have two things. I have two presentations that I prepped. One that kind of goes over what you guys just intro, which is hypersonics, and then a little tidbit about Halo. Let me go ahead and see if it lets me pull that up. Awesome. Can this be seen? Perfect. All right. So I wanted to start off with some vehicle definitions, because hypersonics in a technical sense is actually just a regime. Basically, it's a regime. We've set the floor for that at Mach 5. Anything above that is considered hypersonics. But when you put that in the context of weapons, it's actually very, very different. It's not just about hitting those speeds. It's actually about being capable at those speeds as well. So there's two large class of hypersonic vehicles. The first one is a hypersonic glide vehicles. These are launched from a rocket just before they glide into their target. And then you have hypersonic cruise missiles, which are powered by a high-speed air-breathing engine after they acquired their target. What's important to note is that hypersonic weapons do not follow a ballistic trajectory, and they can actually maneuver en route to their destination. And this is what makes them very strategic and capable. Another thing is to note that terrestrial and space-based sensor architectures are still insufficient to detect and track hypersonic weapons with necessary accuracy and warning. So there's been a lot of development in the defensive side of hypersonics, and there is some sensing capability, but not enough warning to give the adversary time to figure out what's coming their way. This is kind of a chart that kind of puts that into perspective. Below is a hypersonic glide trajectory, and at the top is a ballistic missile trajectory. That target area that you see there, that's what they're capable of sensing, and you can see that line, a hypersonic glide trajectory that's inside of the atmosphere, gets detected much, much later. And this is what makes it so important. Note, the sensors won't be able to tell until it's way too late. So some programmatic differences. Unlike China and Russia, which are the main adversaries here, hypersonic weapons and U.S. Are to be conventionally armed. So they're not being targeted for nuclear armed warfare. And this requires that every single vehicle system, every single onboard system, heat management, everything requires much greater accuracy and fidelity to manage. And this makes it a much more technically challenging problem to solve than to just put a rocket on it and go fast. The counter to that being is that if you did have a nuclear armed warhead, if you're 10 to 100 times less accurate, it's not that big of a deal because your blast effects are going to hit your target no matter what. Let's see. These are the main U.S. programs. The Navy has CPS, the Conventional Strike Program. And they also have HALO, the Hypersonic Air Launch Offensive Anti-Surface Warfare. The Army has the Long Range Hypersonic Weapon, LRHW. It's also internally known as Dark Eagle. And then the Air Force has HACM, the Hypersonic Attack Cruise Missile, which spurred off from Arrow. The Navy currently has they use a common hypersonic glide body, and they actually want to develop this for use across all the other services. So it's something that they can offer to the Army, to the Air Force, for whatever platform they want to put on that common hypersonic body, which is where CPS exists. And it's expected to pair with almost any all-up round or AUR for both the Navy and Army, which is the systems that they're targeting. It hasn't had a successful flight test that is known to us. I've actually heard that there has been a successful flight test, but to my knowledge, what's available to us publicly, it hasn't. But they are planning on fielding this in 2027 on somewhat class destroyers. HALO is compatible with F-18 fighter jets, and the Navy has requested $178.6 million for 2025 for HALO and research, development, and testing, which is very, very very, very unique. All right, here we go, now loaded. The Army, this is Dark Eagle. This has been the most exciting development in hypersonics in the United States. They have done quite a few successful tests. And what's important about this test as well, before I even dive into some of these bullet points, is that the logistics and operations has been also put into place. So how this will be fielded, how it will be deployed, a lot of thought has been put into that. This targets a range of 1,725 miles, which is a large range, which makes this very, very strategic. And they've requested $538 million for LRHW in 2025 and $744.2 million to work on procurement, which is a very, very big step for hypersonics, is funding for procurement. The Army has fielded quite a few of these already and has test fielded these, so this is really exciting. The Air Force, the AMG 183 Aero, this is also the foundations for HACM as well. This is an air-launched hypersonic glide vehicle. Their big target here was actually bomber deployment, and how many of these can actually be fit into a bomber. I believe in a report, 20 of these being equipped in a bomber was a target. This is capable of anywhere between Mach 6.5 to 8, has a range of about 1,000 miles. So it's very, very capable, knowing that it's launched already from a vehicle that's flying. They've actually done a successful captive carry test and had 3 successful tests in flight tests in 2022. There was a failure in 2023, and then they did a test in 2024 with no report, and they actually did not request funding for Aero, and instead all of that has been biased towards HACM. So I'm not going to go into this table, but I did want to show how large, one of the big things in the U.S. is the testing infrastructure. But in actuality, there is a lot of testing structure in the U.S. It's just all booked up. So you can see that both the hypersonic ground testing facility and DoD air breathing open air ranges, there's quite a lot that the U.S. has access to for testing. And then if you look at non-based U.S. infrastructure, this is academia, national labs, there's quite a bit as well that's available to us. Overall, there's about 37. This is a chart on the funding for CPS, HALO, LRHW, and HACM. You can see the proposal based in 2025. None of them actually hit the billion mark, but the CPS has the largest ask for $904 million, which is that they're targeting that 2027 deployment. And then you have LRHW, which is the other big one from the Army. And then this is the procurement. You can see CPS has asked for $0 in procurement for from the Navy, and then the Army has asked for $744 million. All right, so some big statements from China and Russia. China stated that the most important reason to prioritize hypersonic technology development is the necessity to counter specific security threats from the increasingly sophisticated U.S. military technology. And then Putin has said that the U.S. is permitting a constant, uncontrolled growth of the number of anti-ballistic missiles, improving their quality and creating new missile launch sites. If we do not do something, this will result in complete devaluation of our nuclear potential because they would all be intercepted. So I like this. In U.S., we like to think that they're ahead of the game, but at the same time, they're looking at us and they're saying, well, they're further. That's why we're spurring up testing. So in a sense, I sometimes take this as a compliment, even though it is a worry. Russian programs, they got two main programs, the Avant-Garde and the Zircon. And they also have the Kinzhal, which is what they call the Dagger. There's some pictures of them. These are ship-launched cruise missiles, and the Zircon. The Zircon is a ship-launched cruise missile. And the Avant-Garde is a launch from an ICBM. These have been reported to have been tested and been fielded already, which is a pretty big statement. And then their testing infrastructure. They have 2 wind tunnels that they utilize and an airfield that where they do all of this hypersonic testing. Now there's China. They have had multiple successful tests of the DF-17. They have also, U.S. intelligence has also reported 1,500 miles of range. They have the ICBM, DFCF, and Starry Sky 2. So they have quite a large arsenal there. And their testing program, this is actually a picture of their air test bed for hypersonics, and their testing program is actually the largest. It is stated that they have 20 times more capable, they can perform 20 times more hypersonic tests than the U.S. They already have 3 vehicle prototypes that they can flight test in a month, and they have multitude of wind tunnels to do all this testing. So it's very, very concerning what they're capable of. Big issues is that there's currently in the U.S. no program of record, so there's no long-term funding. Hypersonic missiles have not been, or vehicles have not been proven to be cheap. So the U.S. will only be able to acquire a small inventory. capability is required in numbers to be strategic, and there's been no strict mission or policy requirements for these vehicles as yet. Also, the industrial base and supply chain is currently not there to support fielding these as well. Then there's the critic saying that if we go up, everyone else goes up in the arms race. So let's see. That's something I wanted to share. That was the inspiration, one of the inspirations for Halo as well. So we're very patriotic at Halo, and let's see if it lets me. Is it letting me share there?
I don't see the share right now.
Okay. Let me try again. Okay, how about now? Awesome. Okay. Won't take too long here. So I wanted to discuss the big problem with hypersonics. The faster you go, you have this shock wave that gets formed. And as that shock wave forms, the extreme temperatures show up at the nose of the vehicle. That causes surface erosion, chemical reactions, boundary and entropy layers, and this viscous interactions. And all of this feeds right into the engine, which makes it extremely unstable to run, causing tons of problems. And this is even outside of the material problem as well, as these things break down. So some main problems to kind of go over is that you have combustion strategies that haven't really changed since the 1950s in terms of scramjet engines, rockets. The materials that we currently have can't withstand these environments. And then to fix problems 1 and 2, you got to use 3, which is development and testing, which brings up the price of everything and creates this pretty much vicious cycle when it comes to hypersonic engines. So what we do at Halo is we actually utilize a technique known as detonation, and it's basically a bomb. So explosion physics give you explosive performance. These are 25% more fuel efficient, 10x returns on performance. It can reduce your system mass because it's much smaller because of the part count. The part count goes down. They can go 2 times further, and the launch cost for these would reduce an overall about 24%. So some of the unique research that we're working on here is a recent test fire. This was actually done in collaboration with UCF, one of our engines, and kind of a little bit of background of us. So far to date, since Halo's inception, we've already done 2,000 engine hot fires and have done both system and subsystem level prototypes. And we have 3 patents that are getting transferred from UCF, and actually it's not on here, but 2 of our own. We do 50K in revenue. We're a startup, so most of our stuff is research-based, and we already have 3 customers, an OTA vendor, and we're currently actually working on a hypersonic testing facility to help alleviate some of the testing needs here. And we're currently have a Space Act agreement with NASA on this technology as well. Our roots are in UCF. UCF, they're the first impossible rotating detonation engine fired up, and that was one of the unique technologies developed there at the university. Since then, we've developed rapid prototyping with 3D printing, and also basically the brains of these engines as well, and the architecture, how they fit in. So from concept to metal to test for us actually takes about a month of turnaround time, which is pretty cool. I'm not going to dive into this, but I kind of want to show the architecture that goes into making one single system, then integrating that into a vehicle. There's over 60 different subsystems that come in together. You put all that, and if one system fails, you got to go back, fix the other, and you get into this loop until you finally arrive at a vehicle. So just wanted to flash this. This is what we use at Halo internally for every single system. A bit about our team. Susanna McKee, she's our COO. She has over 35 years in the Air Force, very well acquainted with what it takes to fly things programmatically. Adam Kotler, he's our CTO and founder. And then I handle most of the data management, and I'm also the founder and handle the business front. Dr. Kareem is our technical advisor from the university, and got a pretty good track record of papers and hours of testing and successful campaigns as well. So I will end that there. And toss it over to the next panelist. Thank you for the time.
Thank you, Jonathan. And just one small question in terms of China and Russia saying that we have all this technology, and that's why they have to do what they have to do. In just your opinion, and we'll discuss this a little bit later, are they more advanced than we are at this particular stage?
Outside looking in, yes, it does seem that way. But knowing some of the stuff that's also being worked on at the U.S. makes me feel like even though we might be going slower, there might be a point where all of a sudden we are just rapidly speeding up and overtaking and accelerating the development once the key thing happens.
Yeah, I talked about some of the budgetary issues and the fact that they've approved a certain amount of money. Is the money now flowing for these type of technologies?
I feel like it's flowing and there's a bit of a dam in the way. But I feel like once, and I say that because, that kind of puts the picture of there's a lot coming once it breaks and the floodgates open up, so to speak. So there are funding streams and they are opening up. I feel like they just haven't completely opened up for this problem.
Here's what I find interesting being in Central Florida. That first half of your briefing for the audience, that briefing was prepared for a congressional briefing, correct, Johnathon?
Yes, I forgot to mention that. Yeah, so yeah, I was prepared for a congressional briefing.
But as we've discussed, if you think about where we're at here in Central Florida, it's almost like a hypersonics alley. And you have Silicon Valley in California, hypersonics alley here. You'd think there'd be a flow of investors coming, given where we're at in the sector and what's happening. Have you witnessed that at all, or do you think it's slow? And then if you could address acquisitions in the government.
The interest is most certainly flowing. We have seen a lot of interest. I think the risk for it is kind of what holds investors back. So there's most certainly, and it's not so much a risk in the technology and in the team. It's more so most of the investors in this space have previously invested in aerospace companies or are coming from that industry, so they know what it takes to get a program of record type prototype ready to go and the infrastructure required. And even though a small team may be able to maneuver very quickly in terms of development, in terms of integration, it's a long haul. So if you're looking for a return in 3 to 4 years, which is what's typical, for an aerospace startup working in hypersonics, that if they don't have a unique business model or unique business plan, that you're not going to see that for 15 years. And who wants to wait that long? So, but that actually comes from, I would say you would put that on the startup to solve that problem and show them that there is that path there. And that's actually why Halo Engines, we've been sort of in stealth mode the past 2 years while we understand the best way to put our foot forward to both help the nation and also make investors interested, knowing that in 3 years they're getting their return.
Thank you, Johnathon. Our next panelist is Dr. Brian Cole. He is the Associate Dean for the Eisenhower School at the National Defense University in Washington, D.C. He is an expert in the field of national security and strategic studies. He also instructs courses in national security strategy and policy, military strategy and warfare, the defense industry, and courses on the hypersonic and directed energy weapons. Prior to his academic roles, Brian had a distinguished career in the U.S. Marine Corps, retired as a colonel after 30 years of active duty service. He serves as an AV-8B Harrier pilot and held various positions, including aviation weapons school instructor, adversity instructor pilot, and director of Marine Corps aviation support and manpower in the Pentagon. He holds a PhD in international affairs from Old Dominion University, a physics degree with an aerospace engineering emphasis from the University of Colorado, and a master's degrees from the U.S. War Navy College, Norwich University, and Air University. He is also an adjunct professor at Georgetown University's Center for Security Studies, where he teaches game theory and international politics. Welcome, Brian, and thank you for being with us today.
Yeah, thank you, Lou. And thank you, Johnathon, for a great presentation. For the last few years, I've been teaching a course at the Eisenhower School where we study the defense industrial base of hypersonic weapons. And as I mentioned in our talk before, that we started and directed energy weapons. But we really did a deep dive into the hypersonic weapons aspect of the defense industry. And the defense industry, kind of loosely defined, would be the DoD, be academia, be the private sector, from the large firms down to even the smaller downstream firms that are making parts or materials. As a matter of fact, you could find some of the students' reports. Each student will do their own paper, then they combine a report. And at the end of the year, they give a presentation on their findings to a panel of distinguished visitors. And these could be VPs of some of these defense contractor firms, high-ranking officials in the Pentagon, or people that work operationally, for general officers or flag officers. So those are available. Matter of fact, I should probably start saying that, yes, I do work for the DoD, but what I'm saying today, these are my opinions and not that of the U.S. Department of Defense. So this is just me speaking today. So we've had the chance to do that, and we go out and visit the firms. We go out and visit the government, the military side, the political side as well. We talk to members of Congress. Again, as I mentioned, we talk to the large firms, the big defense contractors down to the smaller ones. And then also we visit academia. And we've seen some remarkable, studies that are going, research going on in academia, especially when it comes to computational fluid dynamics. So it's been really exciting to see. And also what's interesting about the hypersonic weapons programs that we've seen is there is a move, and I think Johnathon kind of hit on it. I mean, they are coming. Now, there's no particular program of record in place for weapons, operational weapons systems, but they are they are resident in, for example, the Army's Rapid Critical Capabilities Transition Office down in Huntsville, Alabama. And we've gone there and visited them. And we've also had the opportunity to visit with Lockheed Martin's facility where they're making the missiles for the long-range hypersonic weapon system, and the Dynetics, which is a subsidiary of Leidos, the common hypersonic glide body that Johnathon had referred to. Really fascinating to see not just the engineering process of it, but the materials part of it, the fabrication, modernization of fabrication processes. It's really exciting. These things are coming, but they are expensive. They're extremely expensive. And as we know, and especially in these times of continuing resolutions, and even though we have a defense budget that's approaching $1 trillion, it's difficult to spend money on the types of money that's necessary for these types of programs. But nonetheless, right, they're coming, and everything's a trade-off. So there's money going toward them. They have a joint hypersonic transition office in place. And when these programs mature, for example, from the Army's RICTO down in Huntsville, Alabama, the team that is working there, they will move to the production process. So once that acquisition process gets out of the RICTO, they're going to move with it, and this will become operational. And then once these weapons become operational, the hope is for the DoD that you have volume, and then you decrease the amount of unit per cost. But in my course, we also, a friend of mine who works for the Center of Naval Analysis and also a colleague at Georgetown, he develops and designs war games. And he developed a micro war game, part of a series that he's working on called Missile Production. And the students got to work through this war game to see when and where it's appropriate to use a hypersonic weapon, knowing the cost, the standoff sort of targets you would use them for, and then how they would be integrated with the rest of the weapon systems that we currently have. Now, it's fairly abstract, but it gave a good idea of we could how valuable they are, but they're not used for every situation. And certainly we examine the challenges. That is cost to produce these, supply chains, like Johnathon mentioned. The supply system is not there yet for this, labor force, and then testing infrastructure, which Johnathon talked about also. A lot of our hypersonic wind tunnels, for example, need some improvement, and we need to be able to partner with other countries such as Australia. But I'm going to shift from the technical aspect and look kind of at the theoretical aspect that kind of Lou started with here. And I look at how hypersonic weapons might be or might not be destabilizing, strategically destabilizing, which is sort of a broad term. And a lot of that has to deal with, looking at the current geopolitical environment, our relations, U.S. relations with China, U.S. relationships with Russia, and the lack of existing arms control regime, and certainly that for hypersonic weapons. And I started with, this is sort of in my game theory course, but I started with the idea of challenging some of the assumptions that were made throughout the Cold War for nuclear deterrence. And a game theorist, Frank Zagara, and his colleagues 20 years ago even started challenging the ideas or some of the assumptions that were made on why nuclear deterrence held, the status quo held throughout the Cold War. And thankfully it did. And once we achieved mutually assured destruction, right, where the Soviet Union and the United States had a second strike capability, the ability to retaliate on any strike, it did stabilize things. But one of the main assumptions that tended to be made was that conflict was considered the worst outcome. Again, this is going to be somewhat abstract, but so if conflict is considered the worst outcome, and let's say there's two outcomes that you could choose from. One is if a challenger challenges you as state, and you consider conflict the worst outcome, then the other outcome might be then to concede to the demands of that challenger. And by definition, a challenger that needs to be deterred is not satisfied with the status quo. And so if conflict was considered the worst outcome, then it would be natural for a defender, if challenged, then to concede to the challenger's demands. But this is not what happened, right? The status quo held. And so then Zagara and his colleagues, they have worked through this, and they tend to argue that losing is a worse outcome than actual conflict. And then knowing that if the challenger then challenges a defender, and that defender is willing to fight a war and not lose and not concede, then you could end up in nuclear conflict, and we don't know, the risk is too high. We don't know where that could end up. And then the status quo holds. Well, this then leads me to there is this threshold, this nuclear threshold that does exist, and we're trying to figure out, well, why does it exist? Because if you look at the Eisenhower administration, when nuclear weapons were becoming programmed, we had arsenals of nuclear weapons, they were considered just another bomb. Why wouldn't we use them? And thankfully we didn't. I'm not promoting we use these, but there is this perceived threshold. Now, some might call this a threshold that it's established because of moral issues. But whatever the case is, this threshold exists, and we have a very stable threshold, which brings into this idea of the stability-instability paradox, in which it's very, the nuclear war doesn't exist. Deterrence is very stable, but it also facilitates sometimes more conventional fighting below this. And so within that, then I start to think about, okay, conventional strikes, conventional war, conventional skirmishes are more readily, more likely, because people don't want to cross this because states don't want to cross this threshold of nuclear war. What does that mean for hypersonic weapons then? When we have a crisis, if you think about the Cuban Missile Crisis, right? We had a crisis, and we nearly went to, we came close to a nuclear war potentially with the Soviet Union. But in a time of crisis, with compressed timelines of what hypersonic weapons offer, we end up, with, I think, you're more likely to use a hypersonic weapon than you would a nuclear weapon, thankfully. And in a time of crisis, given the compressed timeline of nuclear weapons and the inability to make decision-making and the operational environment where you have misperceptions, misunderstandings, you might then generate this incentive for a preemptive strike. And this is something that Schelling and Morton Halperin wrote about. Thomas Schelling and Morton Halperin wrote back in 1961 in a book, Strategy and Arms Control, where they discuss this idea of an incentive for a preemptive strike. And this is not a preemptive strike is not to gain an advantage necessarily, but it is based on the idea that conflict is coming, right? And so you have the incentive to strike first, or you wait for your adversary to strike. And given in a crisis, right, again, compressed timelines of hypersonic weapons and the attributes that Johnathon talked about, they fly lower, so they're harder to detect. They can maneuver, so we don't, a ballistic missile, we can calculate, most countries can calculate the impact very closely within a few minutes of launch. It's very difficult to do that with a hypersonic weapon. That's why they're designed that way. And so with these understandings, I said misperceptions, misunderstandings, miscommunications. And then on top of that, you add things of modern warfare. Everything is being compressed in modern warfare, right? Think about anti-satellite weapons, what that will do to communications, what that will do to your operational picture for a commander on the battlefield or at sea, cyber attacks, the implementation of artificial intelligence. I'm not sure where that's going to be going. You combine all of these things, and then you can see where a party may be incentivized to strike first and not receive that particular strike. And I think this creates a rather destabilizing environment. And so, and Lou, like you talked about in the very beginning, the lack of kind of arms control. We know the INF treaty don't have it. The ABM treaty, that's gone. The New START, well, essentially it was 2023, the beginning of 2023, that was gone as well. So we don't have an robust arms control regime. We don't have communication with diplomatic, strong diplomatic relations with Russia at the moment to codify these kind of things. And we don't even know what this would actually look like. But eventually, we will have operational hypersonic weapons. They will be on ships. They will be on land, wherever the Army plans on putting them. And this could lead to I think potentially a very destabilizing environment. And so my original questions were, does the stability-instability paradox apply to hypersonic weapons with either the US and Russia or the US and China? And, it'd be very difficult to understand, for example, where nuclear deterrence is headed with this kind of tripolar nuclear power structure that we have. And so, where is this going to lead with hypersonic weapons? We I'm not quite sure, but I am a little bit concerned about it. And so the second question was then, do hypersonic weapons under the current conditions and increase the incentive for preemptive strike in a crisis? Well, the problem is that they offer an alternative, right? Hypersonic weapons definitely offer an alternative to strike, an imminent target. They can strike a high value target. They can strike, nuclear C3 nodes. They can strike fleeting targets, they're still more likely to be used to strike without having to without fear necessarily, right, of crossing this nuclear threshold. So I think when we see these on the, on the battlefield, so to speak, that, without an understanding of, how they're supposed to be applied, without an understanding of what type of weapons are being used. For example, when Johnathon talked about that China and Russia have ambiguously stated that some of their weapons may or may not be nuclear armed. This creates more instability. The U.S. has unambiguously stated that we will not have nuclear weapons on them. So this is my concern. And without the, with the ABM, the Anti-Ballistic Missile Treaty, gone, the INF, the New START, our arms control regime and our ability to create an environment for arms control and an understanding and communication across the countries creates potentially a destabilizing environment, which has the potential then to have a hair-triggered, event potentially lead to war. anyway, that's where I am right now, and hopefully we'll have strategists and policymakers and decision makers working on these issues. So,
Thank you so
back to
much.
you.
Thank you so much, Brian. I mean, one of the concerns, that is happening is the proliferation of this technology. Okay, in other words, with Russia potentially helping other bad actors also help to develop their particular hypersonic missiles. For example, Iran comes to mind. And to the extent that you had a very few parties, let's say initially having nuclear weapons, and with the proliferation of nuclear weapons, and now the proliferation of these type of weapons, which can be armed. And I'm kind of surprised that anyone would make a statement that we wouldn't. I hate to say this; sounds kind of terrible. I'm kind of surprised to say for the U.S. government to say that we would not use it. I wouldn't make the statement that I would arm hypersonic weapons, but at the same time to make a statement that we would never use it. I don't know. It's kind of crazy to me. So I find this an extremely dangerous situation, and as I indicated, and part of the reason why we're having this forum, let's say, is the use of the weapon. Okay, the use of the weapon, and listening to Johnathon and listening to you and listening to the economics and all the rest of that, the fact that we're not cutting edge in this particular scenario, nor have we fielded enough weapons, let's say, to counter some of these things, or at least have people to realize that if they use their weapons, we have significant weapons to take care of them, is a very disturbing and situation to be involved with. Anyway, if you can, Eric, introduce our next panelist or ask the question of Brian before we start the open conversation.
No, just something to keep in mind for the later conversation. We have hypersonics we're behind, and then you actually have countermeasures. So there's a whole discussion on that and what that means both in acquisitions and in line. We can discuss that after. For now, I'd like to thank Rachel for attending our panel and introduce her to anyone watching. Rachel Hytovik is a doctoral student at the University of Central Florida, a common theme. Three of us are in the greater Orlando area. She graduated with her Bachelor's of Science in Aerospace Engineering from the University of Central Florida in 2020, and is expected to graduate with her PhD in Aerospace Engineering this fall. Her research is directed under Dr. Karim Ahmed at the Propulsion and Energy Research Laboratory. She primarily studies combustion fundamentals for hypersonic propulsion devices with a focus in detonations in flame acceleration for liquid and gaseous fuels. Welcome, and I will hand it off to you. Thank you for attending.
Hi, thank you. Yeah, so I'm Rachel. I work with Dr. Ahmed at UCF. I guess when it comes to the field of hypersonics, I work a lot more on the science and technology side, on the very basic research half, not so much on the applied half of where it's going, but kind of looking at some of the problems that we have and making sure that we can optimize them as such. So I don't work on any like tip-to-tail vehicle design. I work very much on the basic research side. And I can go over some of the kind of advances with that in operability. And so most of it I'll pull up some slides, but most of it, when we have like what Johnathon was talking about with these engines that we want to work on, we want to really make sure that we can optimize them on the materials side, which is not really what I work on, but also on the limit side to look at kind of how we can have smooth sailing when it comes to the vehicles. So I can go ahead and share a few slides to kind of show that. So if you see here, on my screen, the right side is kind of this RDE that Johnathon talked about a little bit. He showed a case of the hot fire of. And what I do mostly is I look at what's actually happening on that front, and I try to figure out, why it's working and why it's not. And Johnathon mentioned, we can make them work. We can have these vehicles operate as we need. But in order to fly them accessibly, we want to really understand the ranges and the failure limits of kind of how that happens. And so what I do is I take this area and kind of flatten it out into just a channel. And I take really fast pictures of it, I guess, in the most simplest terms. So Dr. Reyes worked on diagnostics a lot, and I've kind of extended some of that. But basically what happens is what we can do is we can slow down that, or we can, speed up how fast we look at it. And if we do that fast enough, we can look at the details of what's happening. And so what you're seeing here is kind of this detonation front, as they would call it. And you'll see here that it's not actually like one straight line. It's actually quite a few different little bits of systems. And so Johnathon had mentioned like there's shocks that occur. And this is kind of a shock and a flame coupled and kind of moving around as it pleases. And when all of these things happen perfectly, we get a really good and clear reaction. And we have a good reaction, we have a good combustor. We have good combustor, we have good vehicle. But if we see it happens where we're not seeing a ton of reactions, we're not seeing a lot of chemistry really happening, then we start to have some issues. And so that's kind of where I study. And then to go into that a little bit more in depth, like I mentioned, this is all math side of things, but you have all these things you can kind of parameterize and look at to say, okay, well, if our reaction takes longer, or if our reaction has less energy, or if it's not getting hot enough, or if it's not getting cold enough, we can go from having this really nice detonation front propagate to it not being as nice. And when I say nice or not nice, it's mainly in a reference of symmetry. So we can go from it being like perfectly symmetrical, constantly having a good front, and then kind of go from there, and all of a sudden it stops happening. And then eventually you don't get any reactions. When you don't get any reactions, it's safe to say you don't really have much of an engine happening at all anymore. And so what we look at a lot is, why does that happen? And that gets into a little bit more details on that, which I don't have to go into a ton, but in general, you want to see pretty diamonds, and that's kind of indicative of a really good reaction happening. When you don't see pretty diamonds, then you don't really have a great reaction occurring. And there's been a lot of proof of that. But really, to get to like the main meat of it, what we can say is, in these situations, when I talk about like parameterizing it and trying to figure out what makes it work best, what we find is that, it doesn't matter what fuel you're using. So you could be using a gas, you could be using a liquid, you could probably be using a solid too. But what you need is after you have a shock occur, you need a really, really hot area. And you need a lot of heat release. And so that's probably pretty intuitive. If you want a good combustor, you'd want a lot of heat release. But basically what we find is that we can take any fuel. So right now, these are all gas, but I could replace these with a ton of liquid fuels. And as long as you are able to say, we have a substantial amount of heat release and a pretty hot post-shock temperature, we'll be pretty good to go ahead and operate within an engine. And that makes it a little bit simpler of a problem, because when we've looked at hypersonic vehicles and combustors in the past, it's been a big study of what fuel do we put in it and how do we actually make it fly with a fuel that we'd want. And when we go to run ground experiments, a lot of the times, most people want to simplify a lot of that problem, because it's kind of hard to actually test all of these fuels all the time. It's hard to look at diagnostics of liquid fuels because there's a lot of properties that happen within them. And so if we can simplify it past, like, doesn't matter what fuel you use, as long as it has this amount of energy release, or as long as it has this amount of heat, you can make that problem a lot easier. So that's kind of the side of hypersonics that I've worked on. I've worked a little bit on different type of combustors, I guess. But mostly I work on the operability and fueling for vehicles that don't quite exist yet, but hopefully will exist in the future. Or if they do exist, they're kind of still in like the beginning stages of that. But that's kind of my relation to hypersonics and what I study most of the time. And yeah, so if you have any questions on that or anything, just let me know. But that's kind of where I sit. That's what I do.
Right.
Yeah.
Rachel, what's the best fuel to use? In other words, you use different fuels, as you said, but what in your mind is the best fuel at this point to be using?
So I think when you think of, I think there's two general approaches on fueling. One of them would be, what's the best fuel chemically? And that would probably lead you to say, what's the most simplest fuel? And in that case, you'd probably want to say hydrogen, but realistically, hydrogen has a ton of issues on the production and storage half of it. So then, obviously, if you start looking at how gases leak and how you can actually contain a gas on a vehicle, hydrogen pretty quickly becomes ruled out. After that, I would say a lot of the jet fuels actually work quite well. They have some struggles with air. They have some complications actually getting them to work in systems very well with air. But I would probably tend to say most jet fuels are fine. There are a couple, when you start getting, if you wanted to run ethylene or propane, for example, that would be a gas that kind of doesn't work. But I would say in the liquid side of things, you're pretty open on jet fuel. You get good reactions. It works pretty well.
And what type of temperatures are we talking about when we talk about heat? What type of temperatures are we talking about?
So luckily for detonation engines, once you start heat, it kind of is there. So if you can get the heat to happen in the first place, you need your system to be after your shock. After your shock, you would need it to be around probably like 1800 to 2000 Kelvin. And luckily, when you're moving at a hypersonic speed in most areas, you're gonna get that regardless. So as long as you have a shock that forms that's above Mach 5 or Mach 6, you're likely going to heat your fuel up enough to be okay. It's more so when you get down into like say 15 or 1400 Kelvin, which I don't know what that is in Fahrenheit. But if you get down like into some of the colder temperatures, you might have some issues. But as long as you're hot and your vehicle's moving fast enough, pretty much any liquid fuel should do.
Okay, Eric, I think you were going to say something.
No, I want to say for me, this was a fabulous demonstration. So we have you're here showing a very specific technology area. With Jason, we were talking about building a system. We talk about these technology areas, combining them, the semiconductors, the software, et cetera. And then we discussed with Brian the strategic and geopolitical considerations of. So we had a round. I thought this was a great way to end it, is what I'm getting at, the actual panel presentation, which has a whole bunch of other discussion points on my mind. But I wanted to, for a second, and what keeps coming up in our discussion is that the lab at UCF, if you could address that in more of a general sense, Rachel, I think that would be great for the audience.
Yeah. So the lab at UCF, so I work at the Propulsion Energy Research Lab, which is kind of, I guess, a big topic in a lot of things right now. And it's a pretty big lab, but it has some unique capabilities. So within the lab, we have, I think, probably about 10 different testing facilities, maybe a little bit more, maybe a little bit less. And if we combine all of those testing facilities together, we can get a really holistic idea on combustion and on engine technologies, not just hypersonic, but also supersonic. And so within the lab, we have we can look at standard gas turbines, and we all focus, kind of the lab as a whole focuses on the combustion technology specifically. So we don't do a ton of like aerodynamic problems. There are fluids involved in that, but we're not looking really at like the entire system 90% of the time. But we do look at a lot of the subsystems that would happen in the combustor. And we do test materials. Like that's not a one-off thing. Like we do it sometimes. It's just not entirely the focus. But in the lab, it works well because out of these facilities, we have some that can operate at, say, a higher pressure and lower temperatures, and that works really well for your gas turbine engines. But then we have other facilities that can kind of emulate the flight conditions that a ramjet would see. And then there we can start to look at, flame stabilization of more conventional methods like a bluff body. And then if we go up from there, we then get into these hypersonic test facilities that we've built. And we have a couple of them now, and they're able to say we can match anywhere from, I think, Mach 2 to Mach 7. And we can kind of hit the flight enthalpy within that facility. So we can get to the temperature and pressure that would be representative of that area of flight. And in there, that gives us a pretty big range of things we can examine. Because in that, you can sit in like the scramjet cavity stabilization range. You can sit in the oblique detonation range, which is some of the work that's come out. And then we'll also kind of in that area, then we get into the RDEs. So I think we have probably 3 different rotating detonation engines we can throw on a test. Some of them are for air breathing, some of them are for space. Just kind of depending on who's looking at it and what they want to look at. And then we can go from there and we kind of downscale back and we look at the physics. And so I work on one of the facilities that studies the physics pretty heavily, which makes it really simple as a facility goes, but really important as far as technology and science goes. So we have a couple facilities like that. And then we also have a shock tube to study different interactions. And that one is just your standard, long shock tube, goes to like Mach 9, I think, maybe sometimes Mach 10. And then that kind of gives us this range where we can look at pretty much any Mach number, and pretty much any type of combustion event you might want to see. And then, like Johnathon mentioned, he worked a lot on the diagnostics of it. And so for all these facilities, we have these complementary set of diagnostics that we can throw in. And so we can get into a lot of physics of what's actually happening, but then we can also get into a lot more physics of some of these applied topics. So like if we wanted to look closely on what's happening within an RDE, we have the tools to do so, which is not super common when we look at some of these high-speed facilities. Your ability of diagnostics starts to kind of drop off just because they become a lot more challenging. And it's a lot more of a complex environment where you start to see maybe unwanted effects of diagnostics that you have to overcome. But yeah, that's kind of the lab as a whole. We were able to get this really good idea of combustion, which I think is kind of what's helping us in the past. And we can study pretty much any aspect of combustion anyone wants to study. But yeah.
Amazing.
Okay, why don't we open up the discussion? Everybody can just unmute and we can just talk about any aspect of this, that we want to. My fundamental question is, do we have any operational hypersonic missiles right now? That's really my fundamental question, because it's one thing to talk about the lab and what we're doing with the lab and how we're developing the engines and all the rest of that. While we know, for example, Russia, has actually used one of these, weapons in the Ukraine, and China certainly seems to have them also. What's the thought process on the United States and whether we have operational hypersonic missiles? Anybody?
I will say I think that's a I wish I could say that's a direct answer, yay, nay. But I feel like it depends what you mean by operational. I mean, if you want operational hypersonic vehicle, the X-51 Wave Rider technically is a functioning, operable. The architecture worked, it flew. So the answer there is yes. Now,
when we say that, let me just ask a question. When we say that, what are we talking about? Are there a bunch of these missiles, or just one or two of these missiles, or we just experimented with a missile?
Yeah, I would say there is no inventory. That's probably from
right.
Yeah, from a capability perspective, there is zero inventory, but there are operational systems.
Well, that's what I meant by operational. In other words, are we ready to go? Is really my question. And from what I'm gathering from this discussion, I could be totally wrong. It seems like we're way behind in this particular area. By the time we get geared, we're talking about, a timeline, which I don't know what the timeline is, but certainly I think, Brian, you said maybe it's a year or two from now, basically on having something what I would call operational. Am I wrong on this or what?
Well, I'm not sure of the timeline. A lot of this is funding issues, right?
Yeah.
And so, for example, like Johnathon mentioned, the Aero, the AGM-183, that was a full up round. That was ready to go. The Air Force then just didn't want it, wanted to just complete the test program and leave it at that. But that was as ready a weapon system as you could have. The long-range hypersonic weapon system, the Armies, they have organizational structure for it. I mean, there's no one necessarily there. There might be a staff, but these are prototype weapons, but they're not proof of concept like the X-43 or X-51. They are ready to go, and they just have to go. That prototype will become a weapons program. Now, they're doing some testing. I don't know exactly where they are on testing what they need to what they have left to do on it for the Army, but they have the money and they get through their test regime. That weapon system will be operational. It's ready to go. And then the Air Force, right? They went away from the Aero, which is which is a hypersonic glide body, and they want to go, which was, as you saw the picture, on a B-52. They'd like to go with a hypersonic cruise missile. I've seen it. I've seen the scramjet engine. It's great to see that thing, but it is that's much further behind than the Arrow.
When we talk about supply chains, and let's say these things are ready to go, I mean, what does that really mean? In other words, you know, are we geared to go into production if we had the money, or if the money, you know, came in? I don't know. It seems to me that there may be issues. Are there particular materials that have to be used for these particular systems that are problematic at this time? If we said, let's go, we have the money, let's proceed. Is this an issue? I'm just curious. I just don't know too much about this, guys. What's the thought on this?
Yeah, I think from a technical perspective, the supply chain for materials is not totally there just yet, and sadly, the material issue is not one that you can say, here's $10 billion. Okay, let's figure it out next year. Because even if you are able to do all the science you need to develop the materials, now you then need to involve manufacturers in saying, okay, this is how we can actually build these systems. And then on top of that, that would be specifically for, let's say, a combustor, the materials utilized there. But then the materials you would need on the airframe are different than what you would need in the combustor. So on and so forth with the sensors as well. If you want to get down into semiconductors, right? Your typical silicon chip is not going to be very effective inside of a hypersonic vehicle. You need to go with something more unique like gallium oxide, and that becomes a very, very different problem. So it's not so much here's all the money, the problem gets solved. As much as it is, the money will allow for people to test much more rapidly, and look into things much faster. And I think, assuming money's not the issue, give it a year and a half, then I feel like the answer is a very different question. I mean, the answer is very different than the question.
So what materials do we need? I don't want to go into any super details, but like, what type of materials do we need? Do we need special type of steel, alloys, besides semiconductors and all this other stuff? What do we really need for the material?
Yeah. Well, I could tell you, Rachel knows for a fact that if you're utilizing detonation, any typical alloy that exists today isn't going to be the survivable type for those types of engines. And I can tell you from my own experience at Halo with our own architectures, that what it comes down to is very, very unique alloys, specific to what we're doing and what our engines. And that's the propulsion side of things. And most of it requires 3D printing. The beauty of it, if you're using a unique 3D printing process, is that you can make the powder for the alloy, and then the very, very high heat from a laser can then turn that alloy into the solid that it needs to be, which makes that unique. And then you can print your engine from there with unique architectures versus a typical subtractive.
Are these alloys available?
Yes, and in low quantities. But yes, they are available.
Okay, and where are they? Do we have the facilities here in the U.S. to have these alloys, or do we have to buy them from somebody else like China?
There's only one facility I can tell you of that is working.
Don't give me the address.
Yeah. There is a facility that I can tell you of that is uniquely working on. Any other name drop that I have will violate NDAs. But
don't do that, please.
Yeah. NASA specifically has a very, very strong materials program targeted towards rocket and detonative combustors, and specifically for that in terms of that. Now, there are other programs for other systems on hypersonics, but that's specifically for propulsion.
And geographically, you're speaking to the Space Coast, correct?
Yeah, this actually is NASA Marshall where that work is being done.
Okay.
At their space flight center. That's where they do all of their engine testing. So,
and of course, on the tip of all this, or the back end, depending how you look at it, you have the acquisition process of the government, which, as we all know, is molasses. So, Lou, we're talking about lagging in fundamentals here, but the acquisition process could be corrected before
No,
we get
I
there.
no, I know, but you can have emergency type setups to bypass the system. There's no doubt in my mind that when you're in a particular situation that you could do this. My question is once we have the money and we had the need to do this and it became fundamental, how fast can we go? And when you have issues of supply chains, et cetera, which we know about, that becomes a problem. Let me ask you another question. What guides this missile? What are the elements of the guidance of this missile? How does that work? Does yeah.
It's not GPS, I'll tell you that. Right?
No, I know. And my next question is, can this be compromised? Let me what's your thought, Eric, on this particular scenario?
So this is all public now. You can talk about it. So you have
we only want public information. We want nothing else. It is discussion.
So you have Salt Typhoon. So I have a telecommunications background, and I'm involved in cyber. And right now you have Salt Typhoon by the CCP. Basically, has infiltrated all of our telecommunications. And I just read a release. I believe it's on Breaking Defense, one of them. It got in other news outlets about what can happen to our ports, et cetera. Subsequently from that, there's a release from one of the sub-elements of the space agency about, as I mentioned earlier, about cyber intrusion into these disconnected environments, aka command centers, for these types of capabilities. And everyone's well aware of it. That's why they have some things called zero trust. So the answer is yes. And there's a whole thought process that has evolved called zero trust. And the answer is those capabilities are rolling out as we speak. And there are those that look at it as a practice and those that are just trying to sell things in. And it in and of itself has evolved. I guess I could say consider some of the trusted stakeholders in some of the discussion. But yes, they can be compromised.
Can these be taken over? Can these be taken over? In other words, the launching pad? I'm just curious.
There are cyber capabilities, and this isn't public, also deployed on satellites, right? So for defensive cyber operations. So that's up in space. On the ground, there's deployed on ground systems also. So yeah, the reason they're deployed is they know now that can happen.
What about the deterrence to this thing? Let's assume that we don't have these operational weapons, but other countries do. Let's say Russia, let's say China, and some actor, let's say, this is not part of the war games thing, but let's say some crazy actor wants to use one of these things. Think about the fact whether they can be armed with nuclear, weapons or whatever. What are the deterrents for these type of hypersonic missiles? Any developed yet? Any deterrents?
I don't think we have a good. They're very difficult. I mean, designed to be very difficult to defend against. That's one of the great attributes of these. They are very challenging too, especially because they can maneuver endgame maneuvers that are designed to defeat integrated air defenses. So a big challenge. The deterrence. I don't think certainly the deterrence would be in denial. We'd want to have weapon systems that can defeat, our adversaries' hypersonic weapons. But I think where the deterrence lies now is in the punishment aspect of deterrence.
Right.
If you were to use these hypersonic weapons, well, there's going to be some kind of consequences. And they would typically be used toward. Actually, Russia's use of them in Ukraine is a bit puzzling to me because they have to target a building with a hypersonic weapon doesn't make any sense to me.
I don't think they did it just to target a building. I think they did it for just to demonstrate something.
Yeah, that's exactly right.
Live testing.
Yeah, and then how they get shut down too, because the Kinshall weapon is really not. It's not. It's probably not what we would consider a hypersonic weapon, and in the category of having all these attributes. It can fly at hypersonic speeds, certainly, but it's not necessarily. It's more of an air ballistic launched.
Brian, I have a question for you, and this relates to some of the discussions I've had here and overseas, peripherally, informally, I'll say. So these are informal conversations with real people. In your interview, War Games, and I brought the scenario up, and I never get, and everyone kind of looks perplexed. If you get a rogue element in, say, Africa, a very large continent, manage to mask a hypersonic, has that ever been in your war game scenarios?
No. Usually we're thinking China or Russia, right? What would we do with the sort of an actor that we're just using very rogue, like some, like very, an irrational actor, some kind of abstract irrational actor, potentially. No, these are, where would we, to what extent might we use these? I've done, some analysis on Russia and NATO, like in the high, the North Atlantic, the high North, in the South China Sea type of scenarios, like where could these be used, where could they be placed, and when would you use those? It's like, you start to get into a much more complex problem when you have different actors with different motives.
Yeah, the motive calculation. But when you go big continent Africa, masking a facility, and then at a certain time.
Right. There's just real. This has nothing to do with hypersonics necessarily, but there was a war game developed by Rand. It's not really a war game, but and it's a pretty dry game. But it was developed and created in 2017 to help inform the 2018 national security strategy. Or national defense strategy, excuse me. And I would play that with my students. And oftentimes, you had the US, NATO, and some, the adversaries. North Korea would end up winning the game because no one was paying attention to what their objectives were.
Right.
So, they didn't take over the world, but they would achieve their objectives. And
right.
The US was not able to prevent that because they just weren't thinking along those lines.
No, you answered the question actually by running through that.
One of the things that's coming out in the news is Russia potentially, because of its issues, actually, facilitating or giving information in terms of hypersonic missiles, etc., to North Korea, for example, and maybe and/or Iran. Is that something that's coming up in the news at all, or what?
I don't know specifically about hypersonic weapons, but there is, I think the relationship between North Korea and Russia is very transactional. So if they're going to get troops to support their efforts in Ukraine, we can make certain assumptions.
Yeah, in the news, they're advertising one transaction, and that's probably not what the real transaction is.
That's right.
Well, the news basically said something about the Russia and in terms of hypersonics with regards to North Korea. And I think they also indicated, now this may all be BS, of course. We don't know what's going on. But let me ask you a question. Just again to the deterrence side, is there any research being done on the deterrence side with other types of technology, etc., that could potentially stop these type of missiles? Is anything going on in terms of research that anybody knows about?
The short answer is yes. There's actually a lot of work yes, there's a lot of work going into CM countermeasure methods and methodologies for hypersonic weaponry. It's a very unique problem to solve, and how you would approach that. But there is a lot of work. I can't speak to it, but I know there's plenty of work that's being done there, and it's. I had brought that up once, or someone had brought that up once, and they're like, "Are we just going to use a missile to take down a missile?" And it's much more complicated than that, in terms of that. But I will say there's a lot of what's being coined as advanced detection. So, yes, after a hypersonic missile has been launched, you won't be able to intercept it fast enough. But if you could somehow intercept the information before the launch, it allows you to be able to predict the path that it would fly, even if it maneuvers within a certain range. So the detection method is not so much after launch, it is much before launch. So it's more of an intelligence-based approach than it is a counter strategy.
Yeah, but I think that's kind of complicated,
Oh, no, it is.
I don't see anybody figuring that out. I could be wrong.
So there's there's an actual string, I'll say it, not even conversation, it's actually acquisition of capabilities that I know you can, is again publicly available if you read the encrypted defense news articles, sensor capabilities on satellites. Then you have, as we were talking about earlier, off conversation before we got into this panel discussion, energy weaponry and what those sensors entail. So you've got folks trying to seed that together, but I have not seen that end to end.
Yeah.
Can we talk about what energy, what energy we're talking about? In other words, what are we talking about for the audience in terms of energy type systems that can knock out a missile? What are we talking about? What form does it take? Is it like a ray gun? I mean, it reminds me of Reagan again, as I indicated in our conversations before we started today. What form is this energy?
Brian, you had mentioned your thoughts on that earlier. If you could share that.
Yeah, well, I don't know. I mean, unfortunately, Lou, we kind of start to really quickly go into a realm that, it's hard to talk about.
Yeah.
But I don't know. I mean, there was talk, and this is totally just conjecture, and I'm not getting this from any source. Just there was talk about potential of using, some directed energy to maybe somehow just put off, any kind of missile, right? Just to slightly get it off course. That's all you would need. Maybe it would destabilize in its flight, and at those speeds, it could be.
Is this something that happens with light? Is it something that happens with sound? What is this? Does anyone know?
Lou, I honestly I don't know, and it's just I have never actually seen anything. Any directed energy projects specifically aimed at hypersonic weapons.
Being Greek, I'm thinking of Archimedes. What is mirrors? Trying to knock out some fleets.
Yeah, I don't know. Johnathon and Rachel might have a better idea of what.
Yeah, Johnathon and Rachel. Any thoughts on this?
I wouldn't be able to speak on that specific topic, so I wouldn't really know. I can tell you that in my experience with optics, lasers are always going to be faster than hypersonic missiles. But yeah, that's about as much as I could tell you.
Yeah, I don't see a missile knocking out another missile, at those type of speeds.
Oh yeah.
I don't see it even taking off by the time the thing hits. I could be totally wrong, but these are very dangerous scenarios we're talking about, by the way, and I'm just sort of like flabbergasted that there's no super concern about these type of things. I mean, it's almost like, okay, somebody launched a hypersonic missile, no big deal. Nobody really went into it. And part of the reason why we're having this conversation, actually, because I think it's a real serious topic. Yeah. Any questions of the panelists to each other? Any additional questions?
I had one for Brian on he had brought up New Star. And so I believe, I can't remember when I had took a look at New Start, if it was Article 4, Article 5, but somewhere in there it mentioned that if a party believes that the other party is exploring a new type of strategic offensive, that they have the ability to question that offensive with the BCC. But then I believe New Start expires 2026. So even if you were to bring that into question, it wouldn't mean too much by the time New Start expires. So, and this is just an opinion. I was wondering how much you think hypersonics is actually a part in terms of the treaty when it comes to New Start, or if it's just a non-topic at all when it comes.
So that's a really great question. One is, and to my point earlier, was that these regimes, even though New Start was right, it was extended, it's effectively, non-existent, right? Because people have said, "Hey, we're not going to adhere to some of these." There's been some backtracking on that too, but true, these are not necessarily specifically to hypersonic weapons. Though the INF treaty might have been more involved because some of these missile systems are within that range now that the INF treaty had prohibited. I mean, 3,000 kilometers kind of is or what. 2,000, probably 1,000 to 3,000 kilometers, you can effectively use hypersonic weapons quite well. But yeah, so they're not necessarily addressing specifically hypersonic weapons. And I think, and my point was, like without the infrastructure or any kind of regime, arms control regime currently in place, without talking to each other, right? We don't have any kind of controls. We don't have discussions about these things. When it comes to Russia and China potentially maybe arming, their weapons with nuclear warheads, this can be very destabilizing. And so, yes, New START was extended, but it's effectively since defunct since 2023, and we I think headed toward an area where toward a future that if we don't start talking about or developing arms control regimes that include hypersonic weapons, we could end up in a scenario that could be quite destabilizing. But that doesn't really answer your question directly, but this is my concern.
No, it's all right.
It's a serious concern. All right, let's try to wrap it up if we can. We'll start with Rachel. Just some final thoughts on today's session and anything you want to discuss.
I mean, I think like I said, I work a lot on the science and technology side. So as much as I know there are hypersonic discussions going on, I usually don't see that much of them, or I mean, it's not like my daily focus of work. So I think it was really interesting to hear about kind of more of the applied aspect, and like where we're going, what we're trying to do. Yeah.
Well, we need people like you to be developing all these different things, quite frankly, in the laboratories, or we're going to be in serious trouble. Johnathon, some final thoughts, on today's session.
Yeah. I will say Rachel's very humble. She's amazing when it comes to the laboratory work. So she's definitely has a lot of great input. But yeah, I think one aspect that I would like to see is a talent bridge built from all the talents getting trained up in academia, and that's very important for us, for me personally, and also at Halo as well. So that talent bridge is necessary. And two, the sort of arms shake from private and government to sort of solve this problem. I feel like once that can be done, the funding sources open up widely, and a lot of the red tape sort of comes down. So I feel like if there can be an alignment both for the labor force and also from the funding source as well, we'd be blown away at how fast we can move in the United States solving this problem.
Thank you so much, Brian.
Yeah, I would just add that it goes back to your comment, Lou, earlier about having operational capability. Hypersonic weapons are coming, but they're also not a magic weapon, right? They are defeatable. But the technology that's going into this, and I hear like Rachel talk and Johnathon talk, and I've visited places, startups, and Johnathon, you may have heard of Ursa Major. Not sure if you've heard of that startup. And
of course,
their additive manufacturing processes, and being out to Norway and seeing their solid fuel ramjet engines, not necessarily for hypersonic application, it gets to like Mach 4 or something, but still, it's amazing what technology is kind of coming from these weapon systems. But they're not just weapon systems. I mean, we will find uses for all sorts of this technology, materials, engines, fabrication methods. So it's been a really fascinating talk.
Ryan, do we have enough institutions, let's say university institutions, working on these type of issues on the research side, and or what's your thought on that?
Well, the DoD has sponsored a consortium of universities, and there is, to some extent, I can't remember how many, but I mean, there's tens, if not 100 universities that are attached to this. And they get funding, new research, and so there is a lot of effort to plug into academia and develop technology. And so I've worked closely with the University of Colorado. There's a gentleman out there, Dr. Ian Boyd, who is one of the country's superstars when it comes to hypersonic hypersonic research, aerothermodynamic research. And so, yeah, it's out there, and the government is trying to sponsor them to some extent with this consortium. But
Is any of this stuff taking place on a hush-hush basis? In other words, because I imagine at the universities, a lot of this information just flows out into, to everybody.
Well, right now, I don't know, Jonathan, Rachel, what facilities you have and Eric at UCF, but yeah, so to do some of this work, you have to build in the sensitive, you have to build in, physically build in, the facilities in which you can conduct certain types of research. And you have to vet those people who are doing that kind of research.
So they have special access program facilities, and they are cleared, a lot of them.
Okay, so there's clearance for the individuals who are working on these research projects.
A lot of the time, yes, especially here. Yeah.
Okay, Eric, if you can wrap it up for us. Thank you so much for being, co-moderator today. And this has been a fascinating discussion. At least for me, it's been like totally amazing. It's been disturbing, as I said, and why we're having this discussion. But now I'm to a certain degree even more disturbed. No, I'm not, just kidding. Eric.
No, you just echoed my sentiments, Lou, when you mentioned, hey, let's do another panel. I said, great, let's bring a few people in from a local ecosystem. We'll head up, and you went up to the Defense University. I just really want to thank the three panelists for participating. Your insights, I believe, invaluable, and that mixture was perfect in my view. And we'll obviously look at the video afterwards. But thank you very much, all of you.
Thank you to the audience, and this has been a fantastic panel on a very, very interesting topic that people should take seriously. And I think we should do this again in the near future when there's more advanced things taking place, let's say, within this particular field, just so we can keep on top of this particular very important situation that's taking place geopolitically, I think. Thank you again to the audience, and thank you to the panelists.